In this video, we are going to have the 5 corollaries to Lagrange's theorem. The first one is if G is a finite group. See, Lagrange's theorem itself is true only if G is a finite group. So we have to start like this only. If G is a finite group and A is a member of G, then order of A divides order of G. See, what we had in Lagrange's theorem is order of H divides order of G. This is Lagrange's theorem. When G is a finite group, H is a subgroup, order of H divides order of G is Lagrange's theorem. Whereas here, what we prove is we consider an element A in G, and we have to show that order of that element is that divides order of G. So for that, this trick is this tricks that we are going to use, that is, you consider H to be a cyclic subgroup of G. Can any group have a cyclic subgroup? The answer is yes. G, if it is cyclic, definitely all of its subgroup are cyclic. But even if G is not cyclic, we can always find a subgroup which is cyclic. See, for again, you consider this example G, which is S3. We know that S3 is not a cyclic group. That is, you don't have any element which will generate all the elements of that S3. You have this epsilon, alpha, beta, gamma, delta, theta to be members of S3, but none of them will generate all the elements of S3. So you don't have any generator for S3. But we have the 4 proper subgroups, namely singleton, epsilon alpha, that is H1, then H2, H3, this is epsilon beta, H3 is epsilon gamma, and H4, which is epsilon delta theta. So all these are proper subgroups of S3. He doesn't say that all the subgroup that he hasn't considered. So let H be a subgroup. So you can consider one of the 4 subgroups, proper subgroups. So if you consider this, alpha power 1 is alpha, alpha square is epsilon. What is alpha? That can be checked. If we consider alpha, we know that alpha is this permutation. So alpha composition alpha, when we consider, that's our alpha square. So 1, 2, 3, 2, 1, 3. So when we consider this, it is 1 is taken to 2, 2 is taken to 1. So you have this 2 to 1, 1 to 2, and 3 to 3, 3 to 3. So that means you have this to be epsilon. So alpha power 1 is alpha, alpha square epsilon. Alpha cube again alpha, so it will keep generating only this. So H1 is generated by alpha, and similarly we can show that H2 is generated by beta and H3 is generated by gamma, and for H4 both delta and theta are generators. So even though my G is not cyclic, I can always find a cyclic subgroup. So that is the thing that is considered here. Let H be a subgroup, cyclic subgroup of G. Then by the one of the properties of cyclic subgroup, or rather cyclic group, order of the cyclic group should be same as order of its generator. Order of cyclic group should be same as order of its generator. So order of H is equal to order of A we have. But Lagrange's theorem says that order of H divides order of G. So replacing order of H by order of A, you have this. Order of A is different from, order of an element is different from order of a group. Order of group means it is the number of elements present. Order of A means it is the least positive integer for which A power n is identity element. But already this is established that whenever H is cyclic, order of the cyclic group is same as order of its generator. Now corollary 2 says that if G is finite group and A belongs to G, then A to the power order of G is identity element. Now A power order of A is always identity element. That is the definition. But here what is mentioned is a raised to order of g. It is a raised to order of g, that should be identity element. Now by the above corollary, you have order of a dividing order of g. So we must have order of g to be k times order of a. Now you consider a raised to order of g. Replace this order of g by this. So you have this, and that is a raised to order of a raised to k. But a raised to order of that particular element is nothing but identity element only. That's by the definition of order of an element. So you have that to be e. So a raised to order of g is e. Now this corollary will be used. See, we proved this first and then we made use of this to prove the second corollary. We are going to make use of the second corollary to prove the third corollary, and this one will be used to prove the next corollary. So this corollary is due to Euler. The statement goes like this: if n is a positive integer and a is relatively prime to n, when n is a positive integer and a and n are relatively prime, means the GCD of a and n must be 1. GCD, this is the notation. So GCD of a and b should be 1. Now here we are going to consider this group which is already discussed. So un by the definition, un is nothing but all those positive integers which are less than n and relatively prime to n. So this is that collection un. So this is now taken as g, and how many such elements will be present, that will give the order of g. Order of g is nothing but the Euler's phi function, namely phi of n. Phi of n is nothing but the number of positive integers less than n and relatively prime to n. So that is what you have this collection to be. The number of, this denotes what are the elements. This denotes how many. இது யாரெல்லாம் இருக்காங்க அப்படிங்கிறது un சொல்லும், எவ்வளோ பேர் இருக்காங்கன்றது order of g சொல்லும். So how many is the question means phi of n is the answer. What are the elements means un consists of those positive integers less than n and relatively prime to n. So we are going to make use of the previous corollary to prove this one. So order of g is the Euler's phi function we have written, and since a is relatively prime to n, so what are the elements which are relatively prime to n? And of course less than n, a must be less than n. That element will belong to un. So you have a to be relatively prime to n and a belongs to un. So by the above corollary, and remember the elements in un, they behave like. So you have to be thorough with this example, only then this can be followed. The elements in, say for example, if you consider u8, say u8 means what? It is all those positive integers which are less than 8 and relatively prime to 8. So if you consider 1, it is a number which is less than 8. Okay, and that is relatively prime to 8. So 1 will be there in u8. And 2 will not be there because the GCD of 2 and 8 is not 1. So 2 will not be there. 3 will be there. 4 will not be there. 5 will be there. And 6 will not be there. 7 will be there. So u8 is the set consisting of these elements. And this one will form a group. How we have to form the group? Only with the help of the operation. So the operation is multiplication modulo 8. And these elements, they will behave similar to that of the equivalence classes of Zn. So that is the reason here we are using this notation, equivalence class. equivalence class of A. See, actually A to the power order of G here actually means whatever element that you have A in G. In G means G is UN. How are the elements in UN? They are like this. How do they behave? This is how UN is described. How do they behave? They behave like our congruence classes. So that is the reason this notation is written here. So class A raised to order of G. Order of G is phi of n. You have this. That should be the identity element. What is the identity element in this? This is what. So we can denote in some book you can see like this they would have denoted, or in some book they would have denoted like this, class 1, class 3, like this. So you have identity element to be class 1, and this one, the product, okay, it is same as this. So you have this, and two equivalence classes, congruence classes are equal means then they must be related. What is the relation? Congruence modulo n is the relation. So A raised to phi of n is congruent to 1 mod n. So that is what our Euler's theorem is. Whenever n is a positive integer, A is relatively prime to n. A to the power phi of n is congruent to 1 mod n. So what is to be remembered is G has to be taken as UN. That must be remembered, and the corollary. So in the GPTC rule, what is given is only this. So this in turn implies it's a member of UN. And then what is to be proved? This is what we have to prove. So the technique involved, in that part only you have to remember G must be taken as UN. This G must be taken as UN, and you must know automatically that order of G is phi of n, and the corollary is to be used. So this point and the corollary to be used, second corollary, that has to be mentioned, and that has to be, of course, it should be there in your memory, and that must be mentioned in the paper. Now the next one is due to Fermat. If P is a prime number and A is any integer, then A raised to P is congruent to A mod P. P is a prime number. Prime number means it will not have proper divisors. Itself P and 1 are its only divisors. Rather, actually speaking, plus or minus 1, plus or minus P. But here we consider only the order that is here that we consider. So we are not considering the negative sign over here. So if P is a prime number, A is any integer, then okay, now suppose I consider phi, which is a prime number, and A is any integer, then what relation can we have between these two? We can have, given any two numbers, either the GCD is 1 or it is not equal to 1. Only these two possibilities. You have a prime number. You need not even a prime number. You need not have a prime number. Even if you consider any two integers, they can be relatively prime or they are not. So in particular here a prime number and this is considered. So they must be either relatively prime or they are not. They are relatively prime or they are not relatively prime. Suppose we don't have, okay, we will consider the cases. In the first case we have A and P to be relatively prime. Then we have this phi of P to be P minus 1. So by the above corollary, A and P are relatively prime means it will go under this category. So A raised to phi of P is congruent to 1 mod P. But phi of P, we know the number of integers less than prime number, relatively prime to P is number. How many such will exist? P minus 1. So you just substitute that, and at once we will have A power P is congruent to A mod P. So that is the statement needs to be established. So that in the first case, namely A and P are relatively prime, we have the result to be true. Now suppose they are not relatively prime. like in this case, what we have mentioned that 5 is a prime number that we consider, say, they are not relatively prime. Then what can we say about A? What should be that A? Can it be any number? It can only be multiples of 5. If I have A and 3, what we can say, if they are not relatively prime, then what we can say about A, it should be multiple of 3. So if you consider 3, 6, 9, they are on multiples of 3, so we will not have this to be, these two will not be relatively prime. So, or in other words, this 3 must divide A. So that is what is written. If A and P are not relatively prime, means P must divide A. So if P divides A, naturally it has to divide A par P also. So P divides A par P and P divides A, so it must divide this. So by the definition, how A is congruent to B mod N defined? It is defined in this way. This is true if and only if N divides A minus B. So that is, it is definition. It holds in both ways. Whenever this is true, this is true. So A par P minus A is divisible by P, which means A par P is congruent to A mod P. That is, by this you have this. So in both the cases we have established whether they are relatively prime or not, the result is true. Now the last corollary, if G is a finite group whose order is a prime number, then G is a cyclic group. See, all these 5 corollaries are very important. Either they will be applied in the later results, or they can be asked in, so in that way they are very important, or they can be asked in section A or B. They cannot be asked in section C. They can be asked in section A or B. So now this one, order of G is P. And we have to show that G can only be a cyclic group. Now, already we said that even if G is not cyclic, we can always find a cyclic subgroup. So we have H generated by A different from E. That A is different from E. We are considering H to be a cyclic subgroup of G. By Lagrange's theorem, this order of H must divide order of G, but order of G is P. So for a prime P, the only divisors you have 1 or P. So you have order of H to be 1 or order of H to be P. Now order of H cannot be 1 because H is not generated by identity element alone. So order of H cannot be 1. So the other possibility is order of H is P, and that is same as. So both of them are of the same order and one is contained in the other. So H is contained in G, both of them are of the same order, one is contained in the other, means equality will hold good. So you have your G to be equal to H, but H is generated by A and therefore G must be cyclic. So G is equal to H, H generated by A. So that proves that G is cyclic. Now in this solved problem, we are going to obtain the right and left cosets of H in this. Now actually this G is an abelian group, so either left or right coset it is enough we find. So that will give the required answer. So we know already that AZ6 consists of these congruence classes modulo 6 consisting of 6 elements. Now see, find the right coset and left coset. They have not actually asked for the number of right cosets or left cosets. But we have said already that whenever G is finite, the number of left cosets, the index, can be easily determined by this formula. So order of G is 6 and this is of order 2. So we must have 3 distinct right cosets. So now we will enumerate what are they. Now you consider H. With that you are going to left coset we are considering. So either you consider left or right. So here left coset is determined. So you have 0, operation is addition modulus 6, and h is this. So 0 with 0, 0 with 3. So that will give 0, 3 only. And next one, this h is 0, 3. H is 0, 3. So you have 1 to be added with. This is 0, 3. So 1 with 0, so you get 1. 1 with 3, you get 4. So in the same way, the next one, when we consider 2 addition modulus 6 h, left coset of h. If you consider this 2, then again 0, 3 only we have. So this, it is the set 2, 5. Now if you compute 3, you will get again, see, this is 0, 3. So 3 with 0, you have 3. But 3 with 3 is 6. But here is it 6 that we have. So that must be same as 0. So we get back this 0, 3. And similarly here you have 0, 3. So 0 with 4, this one comes. 4 with 7, 4 with 3 is 7. 7 minus 6 gives you 1. So you have again 1, 4. And similarly, this one, if you compute, you will get this. So we have only 3 distinct right cosets, and by the formula also we have got the same. And this G being abelian, there is no need to separately consider right coset. Both will be the same. So there are 3 left cosets which are also right cosets of H in G, as G is abelian. Now this is known to as any 2 left cosets are either disjoint or identical, because they are nothing but the equivalence clauses under the equivalence relation defined earlier. But independently, if you want to prove that 2 left cosets are either disjoint or identical, how to prove it? Now suppose they are identical, then the result is true. Suppose they are not identical, then there must be an element which is common to say AH, and if they are not identical means we have to say that if they are not identical means we have to show that they are disjoint. So suppose I consider disjoint means their intersection should not have any element. Now suppose I consider X is in this intersection. X will be AH and X will be, say, some BH prime, where H and H prime are in capital H. We can write like this. So this gives AH and BH prime. So this on simplification gives you, because we are post multiplying both sides by this. So you get A to be BH prime H inverse. So if you consider AH, you replace your A by this. This H inverse is present in H, so H will absorb this, and so you'll be left with H prime H. Of course this B will be there. Again H prime is also present in H, it will absorb that, so these two will be absorbed by H, so you get BH. AH is equal to BH. But your assumption is they are not identical. Your assumption is they are not identical, and you are getting them to be identical. So that contradiction arose because you assumed that there is an element in the intersection. So there cannot be any element in the intersection, which means they are disjoint. They are disjoint. So we get a contradiction, and therefore you cannot consider an element common to these two left cosets. And these can be tried. We have already determined it for H1 of S3. For H2, H3, H4, right and left cosets can be determined. Here they will be different because your S3 is not abelian. It's not an abelian group. So number will be the same. How many we have? If we have 2 elements here, say epsilon alpha means you have 2 elements. So this one has 6 elements, so 6 by 2, 3 left cosets, 3 right cosets as far H1 is concerned, but they all will be different. And this U8 is not cyclic. This 1, 3, 5, 7, it's a Klein's 4 group. If you form the table, you will know it. So it's a Klein's 4 group. So it cannot be cyclic. Then U9 is cyclic. So you first list out what is U9. What are the numbers? This is what are the elements. And then phi of 9 is how many are there. So we'll first list out the elements. 1 is less than 9, relatively prime to 9. 2 is less than 9, relatively prime to 9. 3 is less than 9, but not relatively prime to 9. 4 is less than 9, relatively prime to 9. And similarly 5, 6 cannot come, 7 will come, then 8. So these are the members of U9. So you have 6 elements. So to check whether it is cyclic, leave alone the identity element. You try with 2. So you find 2 power 1, 2 square, 2 cube. So when you have the right hand side to be the identity element, then that 2 power, that will tell you the order. 2 power, that number will give the order. So, and if already order is 6 and the order of the element is also the same, means that will be the generator. So in this case you have 2 power 1 to be 2, 2 square 4 present, and 2 cube is 4 into, in this case 4 into 2, 8 is present. So you have this, and 2 power 4, 2 into 8, because 2 into 2 cube, so you have 16 on division by 9 will leave the remainder 7. And this one 7 into 2 you have, so that means 14 on division by have we calculated it correctly? You have 1, 2, 3 will not come, 4, 5, 6 will not come, 7, 8. Yes. So 2 power 1, 2 square, 2 cube, all are here. 2 power 4, 8 into 16. 16 on division by 9 will leave the remainder 7. Then 2 power 5, here it is. 2 power 5 is 7 into 2, that is 14 on division by 9 will leave the remainder 5. And then 5 into 2, next one, 5 into 2, that is 10. 10 on division by 9 will give the remainder 1. So order of 2 is 6 and the number of elements present here is 6. So you have 2 to be a generator, and therefore U9 is cyclic. And either that way you conclude, or all the elements which are listed here are given here also. So in here 1, 2, and then 4, here 5, and then 7 and 8. So U9 therefore is cyclic. Now from one of the properties of cyclic group, we can even find the rest of the generators. K will be, what are the numbers K which are relatively prime to 6. If you find that, what is 6? The order of this cyclic group. So 1 and 5 are the only numbers which are relatively prime to 6. So 2 power 5 is 5. So 2 and 5 are the only generators of this cyclic group. Even if you produce one cyclic group, one generator, this will be called as a cyclic group only. Now this one can be tried by you. G is generated by A, and it's a cyclic group of order 6. You are asked to find the left and right coset. This being cyclic, by the property it is abelian, so either you find left or right coset of this subgroup H, which is generated by A cube. So you have only 2 elements in this. One is E, the other one is A cube. Why? Because A cube and then a cube into a cube is a power 6, but a power 6 is nothing but e because order of g is 6. So h is this. And what are the elements in g? The elements in g are e, a square, a cube, a power 4, a power 5 and a power 4 and a power 5. Only these are the 6 elements. So you need to find EH, that is same as H, and then you have to find out what is EAH, left coset means. What is H? H is E and A cube. So you have A power 4 and A square H means you will have A square A power 5. A cube H, when you consider, it will be A cube and E. So this is the same. So only these are the distinct cosets. This one, and this. Only 3. See, order of G is 6 and this is of order 2. So 6 by 2, only 3 right cosets will be there. So these are the 3 right cosets. So what all we have seen this, the important points. Subgroup criterion. What is subgroup? It's criterion examples. Then cosets. And this relation H is equal to HB if and only if AB inverse belongs to H. And this one, whenever order of A is n, and m is any other integer for which we have a power m to be e, then this is least and this is any other. Least must divide any other. So that result. And why these are alone mentioned, they will be used quite often. Properties of cyclic groups. All the 7 properties are to be remembered. Then Lagrange's theorem and 5 of its corollaries. Only of course 5 corollaries that we have. And what are the standard subgroups of a group? And in particular, what is the subgroup of Z under plus that Hn? So these are the points, they must be remembered from this section 2.4. Thank you.